Hello, Dr. Chad McGee again, and let's talk some more quantum physics. Now, in this particular episode, what we're going to look at is how do you take quarks, which we learned last time about quarks in the anti-quarks, so we were talking about the up and the down and the anti-up and the down. Now let's combine them and make bigger particles. So, okay, we're going to target protons and neutrons. Okay? Now, proton has a net positive 1 charge. A neutron has a net 0 charge. Is that it? Okay? So, how does this work? Well, that means that protons, remember when we're dealing with quarks, we've got the up and the down that we're going to talk about. Now there's 4 more quarks that we could go into detail about, but the net effect is we'll just concentrate on these ones because these are the ones that typically make up the protons and neutrons. Now your up quark has a plus 2/3, down quark has a negative 1/3 charge. So that means to get to the plus 1, a proton has an up quark plus an up quark plus a down quark. Okay? So that would be plus 2/3 plus 2/3 minus 1/3 ends up being 3/3, which is plus 1. A neutron is an up quark plus a down quark plus another down quark. So that's a plus 2/3 minus 1/3 minus 1/3, 0/3 equals 0. Okay? So let's draw them out. Okay? Remember last time I drew you what an up quark looks like. So that's going down this direction. We're going to have an outside coil of 3, and then we're going to have 1 inner coil. Okay? So there's our up quark. All right? I'm going to draw another one. 1, 2, 3, 1 inner, and there we go. I'll go over here and draw it up again. 1, 2, 3, and then 1 inner quark, and there we go, or 1 inner coil, there we go. Not 1 inner quark. Okay, so we got these 2 up quarks, now down quark. Okay, 1, 2, 3 coils, then 1 inner coil, then a second inner coil, there we go. Okay, so over here, down quark, 1, 2, 3, 1 inner coil, 1 downer coil. Okay? Doing it again. 1, 2, 3, now 1 inner coil, second inner coil, there we go. So these are our quarks. We have the up quark here, the up quark, and the down quark. This is the up quark, the down quark, and the down quark. Now, we're now going to smash these together and intermix them. In my mind, I represent them a little bit differently than probably what an average person would. So my net effect from this is I come up and I look at how these would coil together. Yes, gluons play into the portion of this, and I'm going to maybe make it a little simplified, but the net effect is you can look at it like this. Okay? When you're dealing with the neutron, you are going to have a set going this way, one going this way, another one going that way, and this. Okay? So these are actually your spin pairing sets. Okay? You've got 2 of them that are spin paired and 1 net momentum vector that is not paired. That is very important for protons. This leads to the stability of the proton and also why it's a plus 1 charge net overall. Okay? Now, let's take a look at what the neutron would be. Okay? Neutron's going to look very similar, except it's got an extra band. Okay? Because of that, we have now paired up this one, and this one. There is no net momentum vector for a neutron. That means that that is a null charge. Okay? Now, in a later video, I'll talk about how that leads to instability. And basically what happens is you go through a process. If these guys do not see protons, in other words, if they don't have an interaction with a proton that has a net momentum vector, that's what we classify as a free neutron. It's not going to be happy. Light likes to have momentum vectors. It wants to do something to make that. And so what it'll do is end up forming a W minus boson, and that'll end up allowing this guy to make a proton out of it. So we do indigo beta decay. Okay, so I do want to bring up that this is your typical formation of a neutron. Now, whether or not this actually is what you actually see in real life, we'll have to test for that someday. Now, the thing is, though, I like this model because it's an easy to explain model, and a lot of people can understand it, right? Now, correspondingly, for everything that we do with matter, we're going to have the anti-form. So let's do the anti-proton. Okay? Now that means we've got an anti-up plus an anti-up plus an anti-down. Okay? So the net effect is you flip these guys. So flip the directional arrows exactly opposite to each other. Sorry. Sometimes I get overexcited when I try to do these. I'm not an artist. I apologize. Okay? I wish I was more of an artist, but unfortunately I didn't inherit that as well. Okay, so there we go with those two. And now, there we go. So that is our anti-up, anti-up, and anti-down. If we mix these guys, what our net effect should be is exactly equal to the proton, except the vectors are exactly opposite of each other. They're going the opposite directions. Okay, this is spin paired, this is spin paired. Notice this is going in the opposite direction. So what should be the charge of the antiproton? -1. Okay, so that tells you and shows you in a graphical representation a means by which you can easily see how these guys could fit together. Well, not so easily, but needless to say, it does kind of explain how do they go. Now, let's look at the anti-neutron. Okay, this is going to be an anti-up plus another anti-up plus an anti-down. All right, so let's take a look here. Anti-up. That's this guy, roughly. These anti-downs. Oh boy, here we go again. 1, 2, 3, and there we go. So then 1, 2, 3, inner looping, and then down. Okay? So there's our mixes. Yeah, I realize that they're not quite so pretty. I apologize. I'm not an artist. I'm just a scientist. Okay? If we combine them, squish them all together, the net representation for that should look kind of familiar. Okay? So the net effect, no, it's not an egg. It is a circle. Okay? So it's going to be like this. Now, why is this important? Well, spin pair, spin pair, spin pair. Antineutrons act just like neutrons in that they have no momentum vectors. Because of that, this also has a net null, 0 charge. So of course this is the anti-neutron. Has a net charge of 0. And it's going to not be so stable unless it has a corresponding antiproton to to which it can reach a relationship with, because it doesn't like, when light's bent together as a particle, it wants to have a net momentum vector somewhere in there. And when it doesn't, it's not going to be happy. It's going to want to do something to undergo like a beta decay or beta positive decay, to which it will get back to where it has something and form something like an antiproton, where it has a net momentum vector. And so because of that, that's why this guy, not the world's most stable product, and this guy, not the world's most, is if it's by itself. When it's bonded with a proton or an antiproton, when you get to these ones, yes, they're going to be more stable. So that's why inside of an atom, you do have some stability. However, not every atom is stable. Okay? When you've got an exceeding large number of neutrons, what happens is you follow the 1.0 rule, which basically means if you've got more neutrons than that, it's not going to be happy, because what's going on is this relationship between the neutrons and protons is not very good. In other words, some of them are not quite seeing the other proton's net momentum vector. And that's why they undergo beta decay to alleviate that. Okay, so that leads to why you have instability for very large atomic nuclei. Okay, correspondingly, and this is theoretical, but it can be pretty well proven, if we were to ever supposedly make a super heavy anti-atom, anti-nucleus, we would find the same thing would happen. That you would have anti-neutrons that couldn't see anti-protons enough, and you would undergo a type of process of decay, except it would be exactly opposite of what we call beta decay. Kind of funny, but yes, this is how that type of system tends to work. Okay, so I wanted to bring up, this is how quarks are used in building up protons and neutrons, and the corresponding antiprotons and antineutrons. And this leads into why we have certain things that undergo radioactive decay. All right, at this stage, I'm going to stop here and let you guys mull this over in your head some, and we'll be talking quantum physics soon.